Finish off on Monday was we had just started to talk about deviations from the second order underdamped system response. Okay, so you should be very comfortable with the second order underdamped system. And also we are beginning to talk about what the step response for the system looks like. And then once we've established what the step response for this system looks like, we're now starting to look at what is the step response for a system that's slightly different than that. All right, so instead of having a second order underdamped system, which we would have if we have poles here and here, we're now looking at the first case where we have an additional real pole in the system and what the effect is. And so we went through kind of some hand-waving expressions in terms of you're going to get the same second order underdamped response, then plus an extra term, and then we're trying to understand whether or not this extra term is going to be inconsequential, or it's going to have a little bit of effect, or it's going to have a dominating effect. Right? And so we came up with some very general rules of thumb for this, and the pole location matters in terms of how dominant this effect is. And so if the pole location is way in the left half plane, essentially no effect to the response. If it's getting close to, if the real part of this real pole is getting close to the real part of the complex conjugate poles, then it's going to have a pretty pronounced effect. And then if it gets really close to zero, it's going to have a very dominating effect. So those of you who are far enough along in the project, who have started looking at the pole zero maps for that system, you'll notice that you have these two complex conjugate poles that are way far away from the origin, right? And you have a single real pole that's really close to the origin. It looks like a first order response. That's because that pole really close to origin is dominating the response of everything. Okay. And so then we kind of tying that into this example in MATLAB that we had to unfortunately kind of go through quickly at the end of Monday's class. So I want to go through it a little more carefully here. That's the solution to the project part 2. Let's get rid of that. All right. Okay, so I wanted to quickly go through this syntax here because I think a lot of you had not seen I went through this really quick on Monday. You had not seen the function ZPK. So ZPK means zero pole gain. And so you pass a vector of the zeros. So in this first case, we have a standard second order underdamped response. There are no zeros, so we pass an empty vector. In the case of the poles, we wanted to have poles at -1 plus or minus 3i. And so we're putting a vector of poles here, -1 plus 3i, -1 minus 3i, and then we're saying we have a gain of 10 on the system. And so that creates, it's just a different way to enter. So if this is more convenient than the MATLAB function TF, use this. If TF's more convenient, you could use TF. It doesn't matter. It gives you exactly the same response or same answer. But just a different way of entering it. And so this is just easier for me to demonstrate where the poles are. So if I were to say, add a new figure, PZ map of G, you would see that the poles are at -1 plus or minus 3i in the system. And then also, just one note as well, so you would, oftentimes when we see, say, grid on, we get our Cartesian grid. If this is a pole zero map, it's actually going to put in level sets of natural frequency. So going back to Monday's lecture, right, we said that level sets of natural frequency are half circles. So this would be natural frequency of 2, natural frequency of 4, natural frequency of 6. And it's also going to put level sets of zeta on the map for you as well. So this is zeta 0.3, 0.5, 0.68, 0.81, right? So it's a nice convenient way to show what the effective natural frequency and damping constant is for that pole location. Okay, but getting back to our comparison. So we were comparing 4 different cases. One is the nominal case. This is a second order underdamped. The next one is we add an additional pole at -10. And we said that if the added pole is really far away from the real part of the second order underdamped system, it's going to have a very small effect. So we're going to expect that this will have a very small effect. As the real part gets closer to the real part, it's going to have a more pronounced effect. And then if the real part is really close to the origin, it's going to have a really dominant effect. It's going to act more like a first order system than a second order system. Okay, and so then we very quickly at the end of the last class, we plotted all of these. So let me zoom in here a little bit and then blow this plot up. Okay, so let's see. That's too bad, I think. Okay, so the blue line, is that correct? The blue line was second order underdamped system. This is what we'll say nominal. Red line is when we add a pole at -10. And you can see that there's very little effect on the response. They're pretty close, right? There's not much difference. This cyan line is where we put a pole at -1. So you can see this kind of has a combined effect of somewhat second order, and it has oscillations in it, but it also has more of looks like kind of a real response, or a real pole response. And then the last one is being dominated by the pole really close to the origin, where this looks like it's not perfectly a first order response. You see some kind of hitches in the response here that are coming from the oscillations in the system, but it's mostly behaves like what we'd expect if we saw just a first order response or having a real pole. Okay. So I would like to tell you that there's like some sort of just like equation you throw in, and it's just going to really quickly show you the form of the response. I mean, there is. It's called the inverse Laplace transform, but that is not very intuitive. That takes, especially when we get into fifth, sixth order systems, that takes pages and pages of notes to get to the bottom of what the response is, right? And so this just kind of takes practice in terms of trying to understand if you have a system that has second order underdamped response, but you also have real poles or real zeros in the proximity of those second order underdamped system response poles, how that's going to affect the response and which one's going to be dominant. Okay, so we'll go through a lot of examples, especially not quite yet, but pretty soon we'll get into root locus methods, and you'll be seeing a lot of these pole zero maps, and we'll start to try to understand what the response is going to look like based off of this map of poles and zeros. Okay, so it takes some practice. I can't say there's like this, method you just plug it in and it's like, magically shows you what the answer is going to be. It does take some practice in terms of reading this. Okay. All right, any questions on that idea? Yes, Justin. So that would be, yeah, so so you are basically saying, so you need magnitude instead in terms of natural frequency, right? Yeah. Okay, so you were saying, if we look at our nominal system here, right, we have a natural frequency of about 3, right, for this. And it's actually a little bit larger than 3 because our poles are at plus or minus 3i, or what, -1 plus or minus 3i. So I thought basically Pythagorean's theorem is something larger than 3. All right, so that means that our real pole is, if we're saying given your situation you outlined, it'd be somewhere in here. This would be somewhere in between the case with the pole way out here and the pole at -1. So it's going to be somewhere in between that response. So we would expect that it's definitely going to have an effect because it's getting somewhere close to the order of the real part of this. Right, but it's still not going to be as pronounced as if the pole is at -1. Yes?
If all of your zeros like cancel out all of your poles, they're all like right on top of each other, what would that end up being?
Okay, so we'll talk about pole zero cancellations in just a second, actually. Yeah, that's going to be, we're going to talk about adding zeros, and then we're talking about adding a pole and a zero toward the end of today. And I think I'll explain a little bit in more detail because that's actually kind of tenuous because it depends on if the pole zero cancellation is the left half plane or the right half plane in terms of whether or not it's very different responses depending on left So if it's a left half plane and you have a pole and a zero really close to each other, they cancel each other out.
But if all of them cancel each other out, then
You have just the gain of the system. It has no dynamics.
okay.
The dynamics are given by the poles and zeros. If they're all canceled out, it's essentially has no dynamics to it. Okay, so that was the addition of real poles. If we look at additional zeros, this is going to have a different effect, but the methods of analysis are fairly, pretty much the same. And so the easiest way to look at this is actually looking at this comparison transfer function in this form. So it's just rewriting second order underdamped system. I've changed nothing here, just changed the form slightly. It's exactly the same equation. And so this is our comparison, and then we're going to say that we have a system with an extra zero, and we're going to parameterize this zero exactly the same way. It's going to be some scaling of the real part of the second order underdamped poles. Okay, so what that means is that we have second order underdamped poles, and then we place a zero at the location alpha, zeta, omega n. If alpha in this case is greater than zero, we're talking about left half plane zeros, and if it's less than zero, then we're talking about right half plane zeros. Okay, so we didn't talk about right half plane poles, because a right half plane pole is going to cause an exploding exponential, which there's no point in comparing that. That's just a crazy response. But this one's a little easier to compute. So the case of the poles, it adds an extra, basically unknown term in our inverse Laplace transform, which becomes quite complicated. In this case, it's actually a simpler inverse Laplace transform to compute. And so if we say that G1 of S is what we had before, we can actually split this up into two parts. Okay, so just going back to this equation here. All right, so we can split numerators very easily. We can't split denominators so easily. Right, so we're going to split up this numerator in terms of 1 over this whole term, and then S over alpha, zeta, omega n over this whole term, right? So two denominators that are identical. Okay, numerator in the first one is 1. Numerator in the second one is S, and then we have this extra gain on the system, alpha, zeta, omega n. Sorry, 1 over alpha, zeta, omega n. Okay, so what this looks like is our normal transfer function. This is second order underdamped. And this is then an additional term. Okay, so using our inverse Laplace transform tables, if we want to know then the step response, C1 of S going to be equal to G1 of S times 1 over S. Okay, so we're going to do then the inverse Laplace transform. All the full details of this are in the notes. But this one we've already done. We did the inverse Laplace transform of this case on Monday. This one, we're multiplying this term by 1 over S, right? So that the S is going to cancel with the 1 over S. So then this is the inverse Laplace transform of basically two complex conjugate poles, which we would have seen a lot in 3260, and we've seen a little bit in this class, right? So this one is something that we're pretty familiar with. And so then our solution is going to look like our standard second order underdamped step response. This is writing it as a single cosine term with a phase shift, plus then a gain. And note that this gain is a function of alpha. And then we have our decay, and then a sine wave. Okay. So in terms of what we have here, we have essentially a standard step response. And then we have additional term. Okay, I do not know what happened here. Huh. Okay, that was unintentionally deleted. Okay, let me. Okay, so the notes go through kind of two different cases, and it's looking at basically interacting cosine and sine waves. The main thing, and it goes through this in more detail, I think the main thing to point out here is the signs on these terms. Okay, so let's talk about that. Okay, so here's our standard response right here. And then we have this additional term, and we looked at two different cases, right? We looked at the case where alpha is positive, that's a left half plane zero. We looked at the case where alpha is negative. So if alpha is positive, that means the coefficient on the sine wave is positive, and therefore this is going to add to the response. And if alpha is negative, that means that the coefficient on the sine wave is negative, and it's going to then subtract. Right? Okay, so this tells us how a zero location, meaning the left half plane or right half plane, is going to affect the response. Okay, so we have some kind of general rules here that we can look at. And so these general rules, given this relationship in terms of adding or subtracting, so this should say if alpha greater than 0, that means left half plane 0, term adds to response, will increase overshoot. Okay, so we're adding a sine wave at the same frequency, and so at least one of the things it's going to do, well, multiple things, is increase the overshoot. And then the other case, if alpha less than 0, this is right half plane 0. Response may start off going in wrong direction. Now I'll put quotes on wrong. So I don't say there's like a right or a wrong, but we have a normal direction. So we usually think of positive step, response goes in the positive direction. Negative step, response goes in the negative direction. If you have, in this case, you have a positive step, you can have the response initially start to go negative before it goes positive. And that's because we have here a sine wave. It has a negative coefficient on it, right? So a negative sine wave starts out going in the negative direction. The sine wave eventually dies out because it has e to the negative sigma dt term here. So this negative direction sine wave is going to eventually die out, right? But it can start going up in the wrong direction. And so I think the best way to explain this is actually showing a few different cases here of what is going to happen. So same idea as before. We're going to look at this in MATLAB, clear everything. Okay, so here's our comparison. And actually, I'll do this with a gain of 1 for this. Here's our comparison. Standard second order underdamped system. And this is going to have what we expect. Right? So this response. All right, and then some comparisons. This is the case of adding a 0. So before we had an empty vector for the zeros. Now we're going to fill this. We're going to have a 0 in the left half plane. Right? So this now has an s plus 1 term in the numerator. If I say step G1, and look what happened. This is I'm showing these are all exaggerated cases here. These are pretty extreme. We have a pretty large increase in the overshoot. This is a crazy amount of overshoot. So with a second order underdamped system, you can never get over 100% overshoot. That's the maximum you can get. If you add a 0, you see that we clearly exceeded 100% overshoot. 100% overshoot would be having a peak value of 0.2, right? And we've exceeded that. So you can actually get something that exceeds 100% overshoot when you have a real 0 in the essentially a bad location. This would be oftentimes seen as a really poor response to the system, having a really large overshoot like this. If we put instead the 0 in the right half plane, okay, adjusting the gains appropriately, So again, this is an exaggerated response. Okay, so what we see is that the response initially goes in the negative direction. Okay, or what we're calling kind of loosely the wrong direction before then eventually going positive. So right half plane zeros, just to note, this ends up being a source of confusion for a lot of students. The poles dictate whether or not the system is stable or not. You can have right half plane zeros in your system and be perfectly stable. All right, it does not affect the stability. It does have some other negative side consequences. Right half plane zeros are seen to be pretty detrimental at sometimes. As homework problem 1 in this case shows, you actually can't get rid of them with feedback control. They just stick with your system. And they can cause the system to go in the wrong direction. So you may ask, okay, Professor Helsley, what type of system would have right half plane zeros? This happens actually all the time. Anytime you have basically really flexible systems, you have right half plane zeros. Anytime you have pendulum, inverted pendulum type systems, you're going to get oftentimes right half plane zeros. So if you think about this in terms of, I don't have anything that's a good example here, but if I try to like balance some sort of like a ruler on my hand, right? And so you can do this. So you can have a ruler in your hand, you can kind of move back and forth, and you can keep it upright. But if I wanted to start walking this direction, I actually have to move my hand backwards and kind of push. Okay? And so that's a really common when you have right half plane zeros, is that you have to move your system in the opposite direction to then go in the positive. So basically the negative direction to go in the positive direction. All right, so these type of systems happen all the time. They happen with rocket propulsion as well, because you have systems that require you to push in the opposite direction to go the direction you want it to. So they're all over the place, but this is kind of your stereotypical response. So anytime you see a step response initially go negative, that means it must have a right half plane zero. Okay, any questions about right half plane zeros? No? All right, and then getting to the very popular topic of pole zero cancellations. Oh yeah, so also just one note here, I forgot to mention this. If you ever see what's called a non-minimum phase zero, this is synonymous with saying a right half plane zero. Okay, and so this goes back to if you were to take the Bodie plot of a system with a right half plane zero, you get a phase, basically a phase distortion in your system. That's different if you have a left half plane zero. Okay, so I would encourage you to go back and look at the Bodie sheet handouts you got in recitation or content from 3260 to take a look at that. But it creates a phase distortion, which we call non-minimum phase. So if you ever see that, that's what it means. Okay. Now the last topic here in this section here. So the idea of what's called a pole zero cancellation. So by a pole zero cancellation, we mean that we have standard second order underdamped system, and then we have, instead of just an addition of a zero, which we looked at before, or addition of a pole, which we looked at 2 sections ago, we've added both a pole and a zero, and they are fairly close to each other. And so the question is, what is the effect of these poles and zeros being fairly close to each other? So we can look at this from kind of methods of Laplace transforms. And what we're saying here is that we have a Laplace transform, C1 of S is equal to G1 over S, so standard step response, where G1 is composed of second order underdamped system, the step, also the step function, and then a pole zero pair or the zero is at negative alpha minus epsilon, and the pole is at negative alpha. Okay, so we're just saying that, now we could have put the epsilon in the denominator, it doesn't actually matter, it doesn't change this discussion at all. It just basically says that we have a pole and 0, they're both approximately added at the location negative alpha, but one is epsilon different, and this epsilon is going to be a small number. Right? So we usually use the term epsilon for small numbers. Right? Okay, so this means that we can separate this response into two parts. Okay, so if we look at s plus alpha and separate this section out, that's s plus alpha over s plus alpha is 1. Right? So if I were to separate this out, I would have, okay, alpha, again, squared, denominator, okay, which gives us our second order underdamped response. So I'm just giving this G of S times A of S. Our nominal response, plus then epsilon, k bar alpha, then this whole denominator, and the addition of an extra pole. Okay, so the addition of the fact that this has an extra pole is not too consequential. The main thing to point out is that the response is going to act like our second order underdamped response plus some extra term that is multiplied by epsilon. Okay, so we're saying that if this is what we're calling a pole zero cancellation, we're saying that epsilon is a small number. Okay, so if this is a small number, then basically the gain of this is small, right? And so the effect is going to be minimal. Right? And so we're not saying we have a perfect cancellation. We're not saying that the pole and 0 are exactly on top of each other. If it's a perfect cancellation, epsilon is equal to 0, and this whole term goes away. Absolutely no effect, but it has an epsilon, there's a very small effect to it. Right? So writing this in terms of notes that you can write down here. So epsilon goes to 0, pole and 0 cancel perfectly. No effect. As epsilon increases, extra term increases in magnitude. So it's increased effect. So if we have what I'm calling pole zero cancellation, but these poles and zeros start to move away from each other, okay, of course they're not going to cancel each other as well anymore, right? So then you have to look at, all right, what was the contribution of the real zero you added? What's the contribution of the real pole? Trying to understand the response. And then increased effect. And then every controls professor's favorite trick question. We'll jump the gun in here and say, right half plane cancellations are unstable. Okay. All right, so the reason why right half plane cancellations are unstable is we had a few questions about this, right? Okay, so what we're looking at here, these are all models, right? And so these do not perfectly represent our system. Okay, so take, for example, the project, right? You have one of the very first things we did, we have a system, and one of the very first things we did, we took this nonlinear equation of motion, right, and we linearized it. So we've made an approximation, and everyone should understand that that approximation is wrong, right? It is not 100% accurate. So we've modified the dynamics to put it in a form that we can more easily work with. And so if with a nonlinear system, we have no concepts of poles and zeros. This is a linear system concept. And so we're already making some sort of distortion of the truth, right, when we do this linearization. So a very common trick question is to say, okay, get rid of this right half plane pole. And students will say, okay, I'm just going to cancel it with the right half plane 0. Well, you're canceling something fictitious, right? So the pole, there is no such thing as a pole because we've done linearization or we've done some sort of model approximation of the actual system. So you never know the actual location of that pole, right? You have a good idea of where it's at, but you can't do perfect cancellation of it. It's just it's a model, right? So, so basically, all TFs are models, not the real behavior. So therefore, you never have perfect certainty of pole and 0 locations. Okay, so it's actually impossible to cancel those out. So even if, so assuming that you're wrong, and say you wanted to have the right-hand pole case of this, so that would look like right half plane pole 0 cancellation version of this. That would look like this pole 0 map. And we say, all right, we have a pole here. We're going to try and cancel this by a 0 that's somewhere close. You're always going to be wrong in terms of where that location is. And the fact that you don't have perfect cancellation means you have a term remaining that blows up to infinity. Right? And so that, over a very brief period of time, is going to blow up to infinity. Right? It's got, the 0 is not going to have any effect on that. Yes?
Would there ever like do testing to make it right and to cancel it out? It's like very problematic. If they're like a very rich company, they can do it.
So we're talking about even like decimal round off, right? So decimal round off in terms of the coefficient gets dwarfed by a right half plane 0, or basically an exponential increase very quickly. Now, I do know someone who worked for, he worked for, you ever seen the Canada arm before? You know what I'm talking about? So if you look at pictures of the space shuttle and the space shuttle you supply, they have this big arm that would go out and grab things and like basically position things in space. They have Canada written all over it. Canada's very proud of their arm. Sorry?
The big inchworm arm that they walk across the international.
Oh, they had one on the space shuttle as well. Yeah. So maybe they had one on the ISS as well. I'm not sure. But anyhow, so he worked on the Canada arm, and he said that that system is actually unstable, but it goes unstable at such a slow rate that they can operate it for multiple hours before they have to go back and reset it and turn off all the motors and everything. So he said there was no way to actually make that system stable. They just got it to be a manageable instability. So there are cases like that where if you have a really specific need and you have a lot of money, you can do things. Yeah, but so that was a case where they were willing to accept that. Yeah. So you had another question, right?
That was my question.
Okay.
Like, could you ever like tune it so it's so close that it would last a long time, and then maybe you can reset it every once in a while?
Yeah, that's the only example I've ever heard of that. It's not a very common practice. I mean, people work on the space shuttle. That's like a rare breed. It's not like your engineer is working on air conditioning control, right? No offense to anyone who goes to air conditioning control, but I mean everyone wants to work for NASA, right? So.
They haven't built a stable fighter since the F-16.
Yeah.
F-16, F-22, F-35, they're all aerodynamic unstable.
Yeah, they use feedback control to stabilize that. Yeah. So a lot of the newer fighter jets, if you were to not have feedback control on them, they would crash very quickly. They're unstable. Yeah. Sorry, Karsten.
So it's possible to add poles and zeros to a system. Can you destroy poles and zeros? Is this basically the equivalent?
This is the way in which you get rid of them. Yeah. Pole zero cancellation. What?
Is that the only way?
We'll talk about feedback control and how that creates effective pole zero cancellations later. One more question? Yeah.
So the left-hand plane, you have everything that goes down exponentially, and then the right-hand
So, but they're additive, right? So they're not multiplicative. Right? All the terms are additive. So if you have something exponentially increasing, it goes to infinity. The other one goes to 0. So you're adding a 0. You're not multiplying 0. Okay, so that's, I think a lot of this, just like I said before, requires a little bit of practice in trying to understand the relationships here. We're going to talk, this is going to be important when we start talking about proportional integral derivative control. Before we get into that, I wanted to briefly kind of, I say, formalize this idea of stability. We talked about this idea of stability being exponentially increasing or decreasing functions kind of loosely, but I wanted to add a little bit more, I guess, formal definitions of this, because it's a little bit more, not much more complex, but just slightly more complex than that idea. And then the last thing is, we're going to get into PID control on Friday. That's a very important topic, and Friday is also the day before spring break, and if history tells me anything, that's going to be the lowest attendance of the entire year. I'm not accusing you of all skipping class in advance, but it's probably going to happen. So, sorry? You do? Okay, so you will be here then, but everyone else, other people may not be here. So we're actually going to, on Friday, we're going to look at steady state errors, and then we'll go back to PID control on Monday when you guys are all back and relaxed and have sunburns and all that stuff. So. That's what you're doing? Nice. Okay, so stability. So this lecture is called Stability in the Routh Array. We are going to be, just like I did last year, as I decided to skip the Routh Array, I'm going to do this again this year as well. Okay, so the Routh Array is, we'll say, everyone's favorite control method because it's actually really, really straightforward. But I also would say it's no longer that valuable. Okay, so the Routh Array was developed in the, I don't even know when it was developed, a long time ago before computers existed. And it was a way to understand if you have a 20-pole system, are the poles in the left half plane or the right half plane using purely arithmetic, right? So a 20-pole system you can't actually solve. Anything over, I think, fifth order or higher, you can't actually solve by hand in terms of where the roots of that polynomial are. And so this is devised to allow you to not solve for the roots, but understand if the roots were in the left half plane or right half plane. It's still taught some places, but really it's not very valuable anymore with everyone having a computer in your pocket, right, in your cell phone. Right? So the notes are all in here. I've left it in because I've taught this in the past, and I decided it's becoming every year less and less relevant. It's still in here, but we're going to talk only about stability. But there's a lot of content here about the Routh Array, which if you want to read it, go ahead, but it's not going to be gone over, and it's not going to be tested on either. Okay, so stability. So just kind of introducing this idea is that we've been looking at transfer functions, and these transfer functions are always we have some sort of polynomial in the numerator and some sort of polynomial in the denominator. So we can generically call these n of s and d of s if we wanted to. And we know from all the work that you did in 3260 and the work that you've done in this class is that if this d of s is composed of a bunch of poles, say I could write this in terms of it has a bunch of poles. So we have s minus p1, s minus p2, on and up. And if we have this numerator composed of zeros, on, we know that we can, using inverse Laplace transforms, whoops, what am I doing? I could then separate this using partial fraction expansion, or your favorite method of doing inverse Laplace transforms, into a summation, right? A summation of S plus P1, S plus P1 in the denominator, S plus P2 in the denominator, on and on and on, right? Okay, so what this tells us is that the poles give the response, and it tells us what happens when we just have even a single pole in the right half plane, right? And so if we have a single pole in the right half plane, say, I'm just picking on one, say this one is a pole in the right half plane, this is going to correspond to solutions that are of the form, say, increasing exponentials, right? So while all these other ones are decreasing exponentials, we're adding something that's a function of increasing exponentials, and so over time, this response is going to dominate, right? And so when we talk about, the old saying, don't let one apple ruin the whole bunch. Maybe I'm too old and none of you ever heard that one. But this is the case of a single pole being the right half plane makes your system unstable, right? You can have 100 poles in the left half plane, one in the right half plane, still unstable. Okay. Right. And so this is going back to this map. We've shown this map a few times before, is that we have basically all these different responses depending on pole locations in the complex plane. And then we have, in terms of stability, we're talking about a pole in the right half plane causing this exponential increase in the system solution. Okay, and so when we say stability, there's actually multiple forms of stability. Two forms of stability that we are going to concern ourselves with. And the first is the one that we've been talking about all along, and this is the regular just form of stability. So given a transfer function g of s with corresponding impulse response g of t, so we're talking about the impulse response here, not the step response. So going back, this is if we put a direct delta function into the system. So that means hitting the system with essentially infinite energy over infinitesimal amount of time, we get some sort of response, g of t. And if we can bound this response by a decreasing exponential, then we say this system is stable. All right, so we have positive constants, beta and alpha. And if this is true, this means the system is stable. And so by that, we mean that we have some sort of impulse response of our system. Okay, so this may oscillate wildly. Okay, but as long as we can write an exponential that's always greater than the absolute value of that function, all right, we call that system stable. All right, so as long as it can be bounded somehow by a decreasing exponential. And so this beta and alpha can be any numbers greater than 0. So this could be a really, really slow decay rate. So this thing may take 1,000 seconds for it to finally decay, but that's still stable, right, by definition. Okay, there's also the more nuanced case of marginal stability. And so we're saying if the impulse response can be bounded by just a flat line. So if we can write a line given by beta that's always larger than this, we call this marginally stable. And then the last one is if g of t cannot be bounded by a constant, we call this unstable in terms of the response. Yes?
Why does beta have to be greater than 0 for it to be stable?
So this is looking at, if we want here the absolute value of the response to be less than. All right, so we could have done the converse of that. Negative absolute value greater than a negative beta, right? But working all in positive numbers makes it easier to look at. Yes.
Like, if you have a response that, like, decreases exponentially, but then at the end it never quite goes to zero, it always, like, you'd see that, right, in real life?
So you're thinking maybe, I think, the step response, where it may have some sort of final value.
Oh, okay.
But if this is an impulse response, and all the poles, we'll say it to where the poles are, all the poles on the left half plane, it will decrease to zero. Okay, so then theorem 10.1 is a pretty basic theorem here. And so, yeah, I'm in within my last minute. This will be the last content I talk about today before I see a fraction of you on Friday. All right, so if the real part of all the poles of G of S are less than 0, then we call this stable. If the real part of all the poles of G of S are less than or equal to 0 with no repeating poles, no repeating poles on the imaginary axis, call this marginally stable. And then lastly, if we cannot claim that all the poles of G of S, and so by this less than or equal to with a line through it means that we cannot make this claim, then we say the system is unstable. So even just one of them, right? Unstable response. All right, that will adjourn till Friday. Again, reminder, I think 10 o'clock, right? Is that right? 10 o'clock, if there's going to be extra office hours, Friday wants to attend. That's it.